So, welcome back, everybody. As mentioned before the break, we will now continue with the master curricula which are offered of the Faculty of Technical Chemistry together with other faculties at TU Wien. And the first program is Computational Science and Engineering, and the presentation will be given by Professor Georg Matzen. He is professor for theoretical chemistry. You have heard about him because he's also giving courses in other master curricula, and he will now tell you more details about this inter-faculty program which is offered here.
Yeah, thank you, Peter. So, Peter has now it's also lighting green. And also the name of the master program, Computational Science and Engineering, which is an interdisciplinary master, thereby involving several faculties here at the TU Wien. So first of all, what is computational science? I have a couple of slides on it, or computational science and engineering. And as the name says, what you'd imagine, you use high-performance computers to sort of simulate cutting-edge problems. And what would cutting-edge problems be? Well, a couple of years ago, it was definitely related to COVID-19. But maybe sometimes I find this high-performance computation maybe a little bit overemphasized, because we can do enormous, you can be enormously successful on a laptop as well. There's been but it's driven a lot by advances in computing. And computing is not just, obviously it's better and better hardware, but it's also better and better algorithms. And recently also this idea of taking advantage of all the data that is available. So if one was to compare classic computational chemistry, and material science, which is what you're closest to, we would try and understand what's going on in an experiment. And maybe more recently, it's moved towards making predictive results, so even trying to do it before the experiment has been done. And of course, this is a much more computationally heavy part of science, and has also moved the focus maybe from theory towards the computational aspect of it, which has a practical aspect as well. And then also handling, of course, there's also a large computational challenge in handling these large data that are now becoming available. One example, maybe to give you an idea of it, is something we published a few years ago, namely the theoretical prediction of a new material with a record thermal conductivity. And it was used as a logo by the TU Wien for a couple of months here. And it's then validated a few years later by an experimental group. So first you know the material exists, but no one had thought of it to use it as a high thermal conductivity material. And we also got into the mainstream media here, and that's sometimes fun to read what people write about it. And one says, why don't you just make the material and then measure the thermal conductivity of it? And this is a special thing of chemistry, maybe, that it's not really come over yet here. You wouldn't ask why didn't you just build the bridge and see if you could drive a truck over it. You would actually, no one is surprised that you need to simulate certain things first. Or it can be an advantage to simulate certain things first in other fields. So what is it? If you try and Google it, what is computational science and engineering, as what holds this field together? So it's obviously computational. And one IEE, a standardization office, defines it. You sort of learn at some point that you should never define something as what it isn't, but that's what they do. It's not experimental and it's not theoretical. So it's not really pen and paper. It has a much more practical aspect to it, but obviously we don't stand in the lab. And maybe if CM had added computational here, development of problem-solving methodologies and robust tools for solution of scientific and engineering problems. if they had added a computational here. It's the problem-solving methodology which I see as developing algorithms, and then it's something that you're not just developing a little code for yourself, you're developing something that everybody should be able to use, so it should be robust. Is a good definition of computational science and engineering. So what will you learn in the master course? So this is, everything should have a Venn diagram now. So 3 circles here. Disciplinary modeling. That's what you come with from your chemistry. That's the questions that you're able to ask as a chemist or maybe as a bioengineer or whatever. That's your specialized interest and specialized knowledge. And then you need some mathematics, and that's especially numerical mathematics, and some computer science to start solving these problems computationally. And that's also how the master program is built. So it has some details here, nothing surprising. Okay, I'll point with my finger. I think the battery is dying. There's 120 ECTS credits, and it's, as Peter introduced already, involves several faculties here at the TU Wien. Of course, I'm here because it involves technical chemistry. And then, as mentioned, you need some mathematics and some informatics. And then there are other faculties which I would place in this disciplinary knowledge, for example, physics or electrical engineering. Good. And this is how, I must admit that when I first heard of this master's program, it's been running for quite a few years now, 8 years, I think. I was worried whether it would end up as a little bit as a Gemischtwarenladen. You learn a little bit of different things, but don't really become good at anything. But I think it's been solved really well. So first of all, as I mentioned, there's a computer science aspect to this and a mathematical aspect. And that's sort of what keeps it all together. So there are some basic modules that you all have to take in terms of computer science and scientific computing. And I'll come back to it, but these will also sort of, a typical question is, do I have to be really good at programming before I do this? And the answer is no. But you should have an interest in it. And then you need some applied mathematics, and then you choose an extra, some Wahlfächer dazu, which are ordered in modules. And maybe it's easier to see, for example, what is offered from chemistry. There's some theoretical chemistry, but also some computational material science, which is offered by physics. And then there's one of the Pflichtmodule here, computer science, where you, for example, will learn to do scientific programming in Python. Good. So is it something for you? Do you want to implement efficient computer programs? Interested in, you don't have to be able to do it because that's what you learn. Are you interested in solving mathematical problems with the computer with an aim of doing chemistry? And a couple of other things. And if you can answer yes to this with a focus on the interest, then it's something for you.
Thank you very much, Georg. As you have seen, it's nearly all faculties which are involved in this program. Only the architects are not involved in this interfacultary program. So thank you very much. If you have any questions, Georg will be available as well for questions. You can ask now, or you can maybe send him. Yeah, please.
There are 3 courses that are sort of focused on the basics of computational, or 3 blocks of courses. And then there are the Wahlmodule, and there's one of them is, that didn't come over clearly enough. One of them is focused on chemistry, one of them is focused on electrical engineering, one of them on Bauingenieurwesen, for example. And you choose 2 of them. As it's not unusual, I would say, to choose either informatics and chemistry, if you come with our background, or electrical engineering and chemistry. But in principle, if you have a strong interest in Bauingenieurwesen, then that's also possible.
Any further questions? If this is not the case, thank you, Georg, for your presentation as well.